Okay. Yes, I know we're pressed for time here at the end. I apologize for that, but we gotta do what we gotta do. So I'm just gonna read this and point out some things. I don't want you guys focused too much on grades right now. I don't want you worried about grades. Everything will be curved. So everything that we do for the rest of the grades in this class will be, you will be graded based on how well you do in relation to your peers. So please just try to focus on getting ready for the tests. They are on Monday. Okay.
We get the first test.
What? You get the first test. 2 of them. Okay, so to start, I'm going to give one final lesson. It is on terminal velocity and drag forces, which is a topic from mechanics. However, when we were doing terminal velocity before, you hadn't dealt with the type of differential equation that we need to deal with, and so we weren't quite ready for it. So I like throwing it in at the end because the differential equation that deals with the drag forces and terminal velocity is actually very similar to the differential equation that deals with inductor circuits or capacitor circuits, as you'll see in a second. And remember continue working on the assignment titled Inductance and Inductor Circuits. We'll have a few days in class this week that you can spend working on that. Again, don't worry about the grade too much. Don't focus on the grade. Just make sure you can solve some of those problems. It is set to be due Friday night. Be sure to watch on last Friday's module Mr. P's AP Physics C review videos, and check out Dan Fullerton's AP Physics C guide sheets. I don't know if you grabbed them on the way in, but I got the guide sheets for electromagnetism. But there is a link on today's module where it has all of them for all the units. They are an excellent resource. I would even use those when I'm doing calculus-based physics in college to help me out. See last Friday's module for access to the 1998 AP Physics C exams. I am assigning y'all these exams as practice. The answers and solutions are readily available, but I do encourage you to try all those problems first. That won't be due until next Sunday night, so you can spend the weekend doing that. The solutions are there. In the same document that has the tests, the solutions are there, the answers are there. It's not like mine are very different, but I've done both of those tests, so I'll upload. I still need to scan them in at the big fancy printer down in the copy room, but I'll upload my solutions to those as well. Again, no gotcha here. I want you to try these problems and then check your answers, but then you do need to submit your work because I do need to get some final daily grades. Okay. Again, that's going to be due next Sunday night. You just need to submit your work. If there's some MCQs that you don't need to show work on, that's fine. Just leave that part blank. You'll get a daily grade for the MCQ and FRQ portions of each of the exams. So that's 4 daily grades. Should be 100 for all 4 of those. If it's not 100, you're being lazy. And I'm not going to cry. I'm not going to bother myself if you're not going to do that. I'm not going to worry about giving you low grades for that. It's easy 400s. The 1998 practice exams are not on AP Classroom. They're linked on last Friday's module along with the answers and solutions. They will also have the AP Physics B stuff. Don't worry about that. That's not even a class anymore. Solve the problems by hand, showing all of your work and upload to the relevant pages on today's module. I do have those pages created today. I did that this morning. The 98, why the 98 exam? For some reason, the College Board says that the 98 exams are considered to be very good representations of what you can expect to see on the AP Physics C exam, so it's pretty good representation, apparently. If you can do well on them, you're likely to do well on this year's actual AP exam. That's why Flipping Physics has videos where he goes through every single MCQ and every single FRQ. Dan Fullerton might, I'm not really sure. But I did link those Mr. Flipping Physics or Mr. P's solutions and walkthroughs on last Friday's module, so you can check those out. And again, I'll upload my solutions as well. Also, Mr. P and Mr. Fullerton have their, I think it's just the FRQs, but on their YouTube pages, they have FRQs worked out for the past 3 or 4 years, for the problems on the past 3 or 4 years. So you might want to check those out as well. Because I know that you don't have any other AP exams you're working on, right? It's just this one, right?
Just.
Yeah.
So yeah.
The guy who does the review videos for AP Econ that we've been watching, he commented on Flipping Physics videos.
Did he?
Yeah, one of them.
He in the YouTube comments, what did he say?
I don't remember. It was like something about like please get in touch with me. We wanna work on something or something like that.
Interesting. Huh. Okay, we are gonna do. Did I put that here?
Terminal velocity.
Oh, mock exams. Did I not put the mock exam stuff here? Oh crap. Wait, hold on. I think it's-
What month you think?
Yeah, we're doing mock exam. Your mock exam will take place tomorrow and Wednesday. Again, this isn't a gotcha. This is what you can expect. Your grade will be determined based on how well you do with other people. It's only going to cover mechanics, so watch the mechanics videos. I'd do that. We're going to do that the MCQ tomorrow, the FRQ on Wednesday. I should have put this in the overview. I don't know why I didn't put it in the overview. So that we have time to talk about the solutions on Thursday and Friday. Okay. So there's that. And then this is where you're going to upload your solutions to the 1998 exams, and then my solutions will be here at the end. Okay. All right.
So technically we take 2 months.
What?
The 19.
No, the 19, that's just practice. That's just practice. It's not an actual exam. Well, it's an exam, but it's not going to be taken like
I
one.
mean, if we take it like any time.
Yeah. Yeah, you can do that if you got the time and you feel like doing that. That's fine. All right. Last lesson for this year. Terminal velocity and drag forces. So I got three different periods of the same motion. Bradley jumps off a cliff, and immediately he doesn't feel air resistance. Right? Well, ignore the sideways motion. He just drops. Okay. Immediately after he begins moving downward, meaning the instantaneous moment in time between when he starts moving and just after that, he feels no drag force, no air resistance, right? No air resistance. So the only force is going to be mg, right? And so if we're talking about step 1 here, or instance 1, we know the net force on Bradley is Bradley's mass times his acceleration. The net force is literally just mg. And that's going to be equal to ma. Bradley's mass doesn't matter. So the acceleration obviously is the acceleration due to gravity, which is what we know, which is what we use whenever we're neglecting air resistance. Jump ahead to part 3. And this is where we're moving at terminal velocity. So the drag force and the weight force are now exactly the same. Okay? So the net force equals mass times acceleration. But the acceleration is 0 because Bradley is now moving with terminal velocity. And the net force, I'm going to define down as my positive direction. And the net force down mg minus my drag force equals 0. And then so I could say, well, now the drag force equals mg. Right? And as a small aside, I'll come back and talk about this a little more in a minute. The drag force is either proportional to the speed of the object in question or the square of the speed. Okay. In certain cases, it simplifies to be directly proportional to the speed. The more rigorous treatment involving more variables, the drag force is typically proportional to the square of the speed. But for relatively small objects, moving through a fluid that is relatively unturbulent, non-turbulent, then oftentimes it simplifies to the drag force being proportional to the speed v. And way more often than not, that's going to be the case on AP Physics C questions. In fact, it's not just the drag force. Sometimes it could be a braking force. You might think that when you slam on the brakes in your car and you start slowing down, that force is constant. It's probably not constant. Very often, the braking force that's actually acting on the rotors on your tires that's causing the slowing down is proportional to how fast those rotors are spinning between the brake pads. Okay? If they're spinning faster, you get a larger force. Okay? So I know we don't talk about that too much, but those forces, very often forces are proportional to speed. And so whether it's, approaching terminal velocity or braking in your car or maybe one of the problems that's going to be on the mock exam on Wednesday, on the FRQ on Wednesday. You're going to treat the drag force as being proportional to the speed of the object. Okay. And if that's true, then we can say, well, if it's proportional to the speed, we can just say that the drag force is equal to some proportionality constant times the speed. Right. And if I say that, then I can rewrite this equation as the proportionality constant times the speed equals mg. Or I can divide both sides by v and say that that speed is equal to mg over that proportionality constant b. And note this is at terminal velocity. So the v here is terminal velocity. Okay, this is an important result. This is what we did this. It's been a long time, but we did that. We studied terminal velocity in this context several years ago, right? When you guys were just 2-3 feet tall. Except for Timothy, he was like still 6 feet big. Are you 6 feet?
I think so.
Yeah.
A little more than that. I don't know.
Okay. So that's easy. That you don't need calculus-based physics for 1 and 2 here. 1 and 3 here. 2, though, note that the faster you're moving, the bigger the drag force gets. So as Bradley's plummeting towards his untimely collision with the giant airbag that's going to keep him safe when he hits the ground, that drag force is going to increase. It's going to change. Therefore, we have to use the mathematics of change, which is calculus. And so for part 2 of the motion here, we would say then the net force on Bradley is going to be Bradley's mass times his acceleration. The net force now is going to be mg minus the drag force. That's going to be mass times acceleration. The drag force we're going to say is proportionality constant b times the speed v. So mg minus bv. This v is now not terminal velocity. That v is the function. That v is the velocity that's changing, right? So you could say b times v of t, right? That velocity is a function of time. The more time goes, the bigger that speed's going to be. And that's going to be equal to the mass times the acceleration. Nothing cancels, but those astute physicers in here might say, hey, what kind of equation is this? It's a differential equation, right? Because I have a function v, and I have a, which is a function as well, right? Because it's going to be changing. But a I can write as dv dt. So I have mg minus bv equals m dv dt. All right? Okay. And so this particular differential equation, I want to solve using really the only one of 2 methods that we learn about in this class to do differential equations. The other one being just saying, oh, that's the simple harmonic motion. The solution's a sinusoidal function, right? It's just a cosine function or sine function. Here, we can use separation of variables. So first thing I'm going to do, and you'll see why in a second, I'm going to divide both sides by b. So I have mg over b minus the v, which is our function, equals m over b times dv dt. What's mg over b?
Oh, that's
Terminal velocity. So I can replace mg over b, which is vt for terminal velocity, minus the speed, v, as a function of time, equals m over b dv dt. And remember, when we solve by separation of variables, we want all the v's and dv's on one side, and we want all the t's and dt's on the other side. And then we just integrate both sides. So I'm going to divide both sides by vt minus v, multiply both sides by b over m times dt. Hopefully I can do that relatively quickly. So I end up with b over m times dt equals dv over terminal velocity minus velocity as a function of time. Are we okay with that? It's just cross multiplying, really. Right? A little algebra. And what I'm going to do now is factor a negative out of the denominator because it's going to make the integral, at least in my brain, easier to see. You don't have to do this if you don't want to, but I like simplifying my life as much as I can, and I'm not as smart as most of you, so I'm going to factor a negative out of the denominator here, so I end up with b over m times dt equals negative dv over v minus vt. We okay with that? I'm not going too fast with the algebra here. Factor out a negative 1 out of both those terms, and then that negative I can just move up to the top. And then I'm going to multiply both sides by negative 1 so I can get this to be positive, because this is going to be easy to integrate, right? This is going to be a little trickier, so I don't want negatives complicating things if I can avoid it. So I'm going to multiply both sides by negative 1, or divide both sides by negative 1, whatever you want to call it. And I'm going to flip it too, so I'm going to have dv over v minus terminal velocity equals negative b over m times dt. Now I have separated the variables. All I need to do now is integrate both sides. I'm going to integrate this side from when v equals 0, from Bradley just jumps off a cliff, till he reaches terminal velocity vt. And not terminal velocity. We want a function, right? So just until he reaches some speed v, right? Which eventually will be terminal velocity. Although theoretically he'll never reach it, right? But in reality he will. And then I integrate this from time t equals 0. Should write v equals 0. To some time t, and that's going to be the easy part. So what's the integral of dv over v minus vt? Natural log of v minus vt, evaluated from 0 to v. That's going to equal, when I integrate this, I just get t, right? Negative b over m t. You with me? You feeling it? Well, here I can expand this out. Natural log of v minus vt minus natural log of negative vt equals negative b over m times t. Yeah, I did it. I'm sorry, did I not say it? And then I can rewrite this as a single natural log, because we know our properties, right? I'm assuming you do, and you're just not speaking up. Right? And this I can even simplify a little further. Natural log of 1 minus v over vt, right? It's positive 1. This is going to be minus v over vt. And that's going to equal negative b over mt. And remember, we're solving this for v. Right? We want a function for the speed between these 2 points, between when Bradley starts to fall versus and when he's falling at constant speed due to reaching terminal velocity. We want a function that tells us his speed at any point in between those. And so to solve for v, what's my next step? E. If this equals that, then e to the this equals e to the that. Right. What's that?
E to the this equals e to the that.
And e to the this equals what?
1 minus v
1 minus v
over vt.
over vt. That equals e to the negative b over m times t.
What's the absolute value?
Just assume it's absolute value. Where's the absolute value go?
That would already be an absolute value.
Natural log of 1. Natural log of the absolute value of 1 over 1 minus v.
V divided by vt is never going to be larger than 1.
Okay.
Right?
Well, no, it could be.
No.
If there's
Not in
external
this,
force
not
on
in
it,
this situation.
there's an external force on it.
Yeah, but we're not going to deal with that in this class. Theoretically, you're never going to reach the terminal velocity. You're going to be asymptotically approaching it.
Yeah, not in this
Mathematically.
scenario, but like if something was like an asteroid coming into Earth that.
Yeah.
Alright.
Yeah. Then you'd have to be a little more careful. And then, so I'm just going to rearrange this a little bit. So I'm going to actually add the V over VT to both sides and subtract E to the negative V over M. So I end up with V over VT equals 1 minus E to the negative V over M times T. And then multiply both sides by the terminal velocity. V equals terminal velocity. And now, just to remind myself, this is a function of time. Our speed as a function of time equals the terminal velocity times 1 minus E to the negative V over M times T. So as T approaches infinity, the speed will approach terminal velocity. Right? And mathematically, according to this, it will never quite get there. But again, this is a model for reality. And in reality, it will get there. Bradley will achieve terminal velocity.
Man, I hope there's a lot of friction.
Yeah. Or that you're just falling through a very, very viscous fluid. Maybe not air. Because it turns out, and I'm going to put this up here just for argument's sake, the more rigorous form of the drag force equation is 1/2 times rho, which is our fluid density, times the speed of Bradley squared, or whatever object traveling through whatever fluid, times a constant called the drag coefficient, times the cross-sectional area of Bradley, or whatever object is falling. Okay. That's the area in the direction exposed to the direction of motion. That's why when skydivers fall and they're falling like this and they're facing straight down, they go to much different speed than they do if they streamline themselves. Same thing for divers, right? When you hit the water, that's the fluid. You're going to reach terminal velocity relatively quickly, right? If you jump in the water. You're going to reach it much more quickly if you belly flop. Because the area exposed to the direction of motion is going to create a much larger drag force, okay? And then so you're going to reach terminal velocity very quickly, as opposed to what you're supposed to do, either going, diving like this or feet first, streamlined. Then the drag force is going to be significantly reduced because you've significantly reduced the cross-sectional area exposed to the fluid that you're moving.
Have you ever seen a video of someone belly flopping off a high dive?
Yeah,
It's like
It's
I wouldn't.
One of the worst things I've ever watched.
Yeah, I wouldn't. Yeah.
Have you seen Cody's last? He was trying to walk on Mercury.
Oh no.
Yeah, that's
Was he able to?
Sort of. I mean, he had to hold on to stuff. I guess it's dense enough you can stand on it.
Well, yeah, you'd float in it.
You can like
Yeah.
slip and fall easily. It's a fluid. But
Yeah, I've seen videos where they'll take like a chunk of iron, and throw it into mercury, and it literally floats on it.
That's so odd.
If you ever fall in the lava, people think they seen Lord of the Rings when Gollum falls into the lava and he sinks. You don't sink in the lava. No, that's molten rock. That's way denser than you are. You're not sinking down. You're staying right there on top.
You're just melting.
Probably more like vaporizing. But anyway. It turns out, though, this drag force is obviously proportional to the square of the speed. But there's another concept called the Reynolds number for a fluid. Definitely beyond the scope of this class, but I just like pointing it out because it is involved with this. For any fluid, there's something called a Reynolds number. If the Reynolds number is small, then you don't have a lot of resistance to the it has to do with ratios of the viscous forces and all this. It's pretty complex stuff. But for fluids with low Reynolds numbers, the drag force ends up simplifying to be proportional to just the speed of the object that's traveling through it. For larger Reynolds numbers, that's where you gotta take into account the more complex stuff going on here. Interesting note, the guy that first started developing what was later called the Reynolds number was Stokes. George Stokes, I think. Stokes' theorem is a vector calculus theorem that you will learn about at the end of vector calculus after you learn Green's theorem. And then you'll realize, hey, that Stokes' theorem is literally Faraday's law. But Stokes' theorem is generalized to any conservative vector field. And the line integral of the boundary of the surface through which the flux, whatever the flux is going. And so So actually, Stokes came up. He started discovering this stuff. Reynolds then developed it further. But Stokes' theorem, telling you now, because Stokes' theorem and Green's theorem gave me a real bad headache because I was learning that stuff before I was learning Faraday's law. Having a little bit of knowledge of Faraday's law and Ampere's law to an extent, once you learn the differential form of Faraday's law, Ampere's law, it should make more sense to you. Like me going, I was learning Stokes' theorem from a purely mathematical standpoint, and I could not wrap my brain around it. I just had to do a bunch of examples, and then it wasn't later until I actually took the calculus-based physics class where it finally clicked. So keep that in mind when you get to Stokes' theorem. Faraday's law is just one application of Stokes' theorem, and the same thing works for any conservative vector field. So
What if it's not conservative?
then
Like, what would you use then?
I don't know where I've ever seen a non-conservative vector field though.
Does it
Vector fields, I think, but I don't quote me on this because I'm again not as smart as maybe some of you. I'm pretty sure that vector fields, by their very nature, are conservative.
Then why do we put the word conservative in front of it?
That's a good question. I might be wrong. I don't know. I probably shouldn't be getting a video of this because I might be totally wrong. I just have never really encountered. Every time I've dealt with a field indicating either forces or fields, they've been conservative, like the electric field, the magnetic field, the gravitational field.
Just thinking about an unconservative.
I don't know. Maybe when you get into QFD, quantum field theory, maybe there's fields there that aren't conservative. I don't know. But that QFD, I'll never understand. So I'm not even going to try. I understand enough about it to know that there's no way. There's no way. You guys, yes. Me, I'm too old. Set in my ways and not smart enough. So. All right, that's our last lesson. Any questions?
There is an article called "How to Determine if a Vector Field is Conservative." So that implies that there are non-conservative ones, I think.
Okay. Cool.
Yeah, take a picture of the board.
What?
Can you take a picture of the board?
No.
Okay.
Only if I can be in it. All right. So yes, those at home, I'm sorry it's not on the overview, but we are doing our mock exam tomorrow and Wednesday. Okay? All right. Any other questions about anything? So what you got to do, the inductor circuit quest, hopefully you watch those Dan Fullerton videos, due Friday night. The 1998 exams, which again, you have access to the answers, so there's no excuse to not get that done, but please try your best on them. That's going to be due Sunday night. That's pretty much all you got to do at this point. Those 4 submissions for the 98 exams. The quest assignment, our last quest assignment. This stuff, notice, sorry I didn't point this out. This is one reason that we don't do this first semester when we do mechanics is because you haven't done the natural log integrals yet. Right? At this point, we know how to do that. And look, this is literally what the current through an inductor is, right? The same equation. You have an exponential growth, right? Because the inductor at first resists that incoming, not the same exact, but very similar, I should say. Resist that current. That current grows exponentially until it asymptotically approaches the maximum current. It's very similar to how capacitors charge and discharge, to how inductors charge and discharge. I put that in quotes because inductors don't really charge. They just store energy within the magnetic field. So it's very similar. Hopefully this isn't too much. Again, the 2 main types of differential equations are actually found in the inductor unit because you see that when you have a capacitor and an inductor wired in a circuit with 0 resistance, then they exhibit simple harmonic motion. Right? Where the angular frequency of that simple harmonic motion, is 1 over the square root of inductance times capacitance.
I thought you were saying there was a bathroom over the square root of inductance times capacitance.
Well, that too. I mean, obviously, there is. All right. That's my story. Mock exam tomorrow. Watch the videos. You can look at past quest assignments. You got the links to the guide sheets from Mr. Fullerton, which are really good. Again, don't worry about the grades. Just do your best.
I'm gonna watch all of Flipping Physics' channel today before the exam.
He doesn't have nearly as much Physics C stuff as he does Physics 1 stuff, but he's still got some good stuff. He's got great review videos.
He only has like 3 videos for E&M, though.
Oh, really?
Yeah.
Oh, okay. He has review videos, though, right?
Yeah.
Review of
But
all the topics.
In my opinion, I did watch a little bit of like his first E&M video, and it's kind of too simplified. Like,
Oh, really?
Just briefly explaining like each equation.
Oh, okay. Okay.
I feel like simplified is better for my brain. Because this feels super simplified.
Well, the goal is you just need a refresher on the basics, and then, oh yeah, now I can apply that to the more difficult problems. Okay. All right, bye everyone at home. See you tomorrow at the mock exam. You gotta show up. You gotta show up on Zoom.